Hi class, I'd like to do another example of separation of variables, this time in 2 dimensions, and again for the heat equation. So here's our heat equation. We're going to let capital T represent the temperature of a plate as a function of its position for all time. Now the plate has length capital L and width epsilon. I've oriented it so that the x-axis is along the long axis of the plate and the y-axis is along the short axis of the plate. The boundary conditions on the plate are as follows. At the ends, at x equals 0 and x equals L, we'll use the same boundary conditions that we have used before and that we're used to. We're going to hold the temperature fixed at t equals 0. So that's what we have here. At x equals 0 and x equals L for all time, the temperature is held fixed at 0. Along the top and the bottom of the plate, however, we're going to assume that the plate is insulated. That is, that no heat is flowing. The flow of heat is related to the gradient, or the derivative, of the temperature. Heat can only flow if there's a difference in temperature. So if there's no heat flowing out of the top of the plate or the bottom of the plate, the derivative of temperature in the y direction has to vanish. So the boundary condition at the bottom, at y equals 0 or at y equal epsilon, our dt dy is equal to 0. This is a new kind of boundary condition that we haven't talked about before. This is a Neumann boundary condition. And that terminology is as opposed to the one that we're used to, where we're holding the value of the temperature itself fixed. That kind of a boundary condition is a Dirichlet boundary condition. So we're going to solve this two-dimensional heat equation subject to these boundary conditions. And we're going to use separation of variables. So we're going to start by assuming we have a solution of the form some function of time times a function of x times a function of y. We're next going to plug this into the equation and see what happens. Plugging in our assumed form for the equation and dividing by the solution itself, on the left-hand side we have a term which depends only on tau dot over tau, where tau dot is the derivative of tau with respect to time, and we put the diffusion constant on the left-hand side just for convenience. On the right-hand side we have two terms. One is the second derivative of the function of x divided by itself, and the second term is the second derivative of the function of y divided by itself. So the equation, when we've assumed the particular form of solution, has on the left-hand side a function of time only, and on the right-hand side the sum of a function of x and a function of y. The only way that a function of time can equal a function of x plus a function of y is if they're both equal to a constant, and we're going to call that constant minus k squared. It's worth emphasizing the units of that constant minus k squared, which are easy to ascertain by looking at the right-hand side of the equation. Equating these, we see that the units of k squared are 1 over length squared. So if we deal with the time derivative first, the equation we get is right here. 1 over d tau dot over tau is minus k squared. It's easy to solve. Tau is a function of time, is proportional to e to the minus d k squared times t. It's worth checking units again. D, the diffusion constant, has units of length squared over time. So d k squared times t is dimensionless, and we know that's correct. Any argument of the exponential had better be dimensionless. Furthermore, our choice of minus k squared appears to be correct, because we would assume that k squared is a positive number, in which case the function tau of t decreases exponentially, which corresponds physically to the fact the temperature should be leaking out of the rod and should be going to 0. So this is the solution of the time part of the equation. If we look at the spatial part, we have x prime double prime over x plus y double prime over y is equal to minus k squared. But this is a function of x only, and this is a function of y only. So the only way that that's possible is that both of these must actually be constants. Let's call the constant for x double prime over x, given that we know what kinds of things we might expect here, I'm going to call that constant minus n squared pi squared over L squared. Again, in this case, the dimensions work out. The L squared takes care of the dimensions of the left-hand side, and so n and pi are dimensionless. With an assumption of this form, the solution, x, is the form a cosine n pi over x plus b sine n pi over x. We now impose the boundary conditions in the horizontal direction. X of 0 and x of L are equal to 0. That gives us the usual thing that we've gotten before. A equals 0, and n is a positive integer. Again, 0 doesn't work because the solution would vanish. And negative integers don't work because they're just minus the solution we had before. They're not linearly independent. We now do the same thing for the y part of the solution. Y double prime over y it's going to be minus m squared pi squared over epsilon squared, where again epsilon is the width in the vertical direction of the plate. So this is a separation constant very similar to what we've assumed for x, but in the y direction instead. The solution y then becomes a prime cosine m pi y over epsilon plus b prime sine m pi y over epsilon. But now we have to impose our Neumann boundary condition. D capital Y dy vanishes at little y equals 0, or epsilon. In this case, it's not the a term which vanishes, but it's the b term, because the derivative of sine is cosine, and if we want this to vanish, then b prime had better be equal to 0. That's what we get by imposing that it vanishes at y equals 0. By getting it has to vanish at y equals epsilon, we find that m is in fact an integer, just as we expected it would be. But now, given that it's only the cosine term that survives, we have to allow for the possibility that m can be 0, as well as 1, 2, 3, 4, etc. Think about why I don't assume it's possible for m to be negative 1, negative 2, negative 3. Now, I've introduced a separation constant for y. On the previous transparency, I had a separation constant for x, which was n. If we plug both of these back into our differential equation, we see that we get a dispersion relation that k squared, k being related to the separation constant in time, is equal to n squared pi squared over l squared plus m squared pi squared over epsilon squared. So we have three different separation constants, one for time, one for x, and one for y, but we have one relation between them, so we have two independent separation constants. This corresponds to the rule that we had, that in 2 dimensions we're talking about a system with three independent variables, x, y, and t. Of those, the equation relates the three constants, so we only have two independent separation constants. We can put all this together and we see that a single mode, a solution of the form a function of x times a function of y times a function of time, has this form: sine n pi x over L times cosine n pi y over epsilon times e to the minus d times the quantity n squared pi squared over L squared plus m squared pi squared over epsilon squared times time. And again, the same calculation we did before shows that this quantity is dimensionless, as it must be, as are the arguments of sine and cosine. Now, the single mode, of course, is not the most general solution. Because of the linearity of the equation, the most general solution is actually going to be a linear combination of these modes. So it's some arbitrary combination summed over all possible n's going from 1 to infinity, all possible m's going from 0 to infinity, of some arbitrary constant, a, which depends on the mode, n and m, times the form, the functional form of the mode, sine n pi x over L, cosine m pi y over epsilon, e to the minus d, n squared pi squared over L squared plus m squared pi squared over epsilon squared times time. Notice that in each mode, the n and the m in the time dependence are linked to the n in the x dependence and the m in the y dependence. That was the result of the fact that the overall mode has to solve the diffusion equation, which relates the time dependence to the spatial dependence. Now, in order to figure out what these a and m's are, we need one more piece of information. We actually need initial conditions. We need to understand what happens at time t equals 0. We need the initial distribution of temperature. If we plug in t equals 0, we see that the exponential just drops out, and we get a double Fourier series of this form, sum over n and m, a and m times sine n pi x over L, cosine n pi y over epsilon, and we understand exactly how we should invert this Fourier series up to overall constants that we can calculate. A and m is related to the integral from 0 to L dx, the integral from 0 to epsilon dy, of sine n pi x over L, cosine n pi y over L, epsilon, times t of x and y at t equals 0. This formally concludes the solution of the problem. On the next slide, I'll make some remarks. Notice that the time dependence of this solution is of this form, the exponential of this combination of things. We were interested in the limit where the rod, the plate, is much thinner than it is long, so epsilon was much less than L. That means that for any m not equal to 0, this term, m squared pi squared over epsilon squared, is likely to be much larger than this term, n squared pi squared over L squared, since there's a 1 over epsilon squared here and a 1 over L squared there. That means if we wait a few seconds or instants, then at longer times, it's only the term with m equals 0 that's going to dominate. Everything else will have died away very quickly in time. That makes sense. The rod was very thin with width epsilon as opposed to how long it was with length L. So any distribution of temperature is going to smooth out over the vertical direction very quickly, and then it's going to smooth out over the horizontal direction. In that case, the two-dimensional problem that we started with, if we wait long enough and only have the m equals 0 solution, reduces to the one-dimensional problem of the heat equation that we solved previously.